Hello, everyone. Thank you for having me here, and thank you for coming to this talk. So, as Misha said, this is going to be episode 2 of Rydberg atom arrays at Harvard. So, in particular, I will talk about some recent experiments where we probe topological phases using this platform. So, I don't need to introduce the platform much because you heard from Manuel and Misha about it. But I want just to have one slide to point out something that I think is one of the remarkable features of this quantum platform based on neutral atoms, which is that when we want to create interesting, highly entangled phases of matter, we have 2 possible approaches to do that. And so we can do it in an analog way. So you can, with this I mean that you can engineer the system Hamiltonian such that the desired phase is somehow encoded in the Hamiltonian itself. Or you can do a digital approach where you actually implement a quantum circuit and a sequence of gates to get to the desired entangled state. And I think one interesting example in this sense is related to 2 experiments that we performed over the past year and a half. And then there is a hybrid approach that also Misha mentioned a little bit at the end of his talk, and that I will also comment about towards the end. There were these 2 experiments recently where we studied Z2 quantum spin liquids, and in one case we did it using the Rydberg Hamiltonian to encode an RVB-like state, and this is what I'm going to talk about today. But then one of the experiments that Misha mentioned towards the end, you saw that we can also do the same type of phase, so a Z2 quantum spin liquid, but in the toric code state that he mentioned with this atom moving architecture. So I think this is one of the interesting features of this atom array platform that I just wanted to point out because I think it's one of the cool things about this array. So in this talk, I will concentrate on this experiment here on the left. And let me start by telling you a little bit what I'm going to talk about. So first of all, I will show you the experiment where we demonstrated the detection of this quantum spin liquid phase using frustrated arrays of Rydberg atoms. Then I will show you how we can use this spin liquid as the base for topological qubits. And finally, I will show you some more recent results that are going to be on the archive, hopefully in a week or so, where we studied how we can enhance the detection of this topological order by using local error correction. So let me start with a quick introduction about the quantum spin liquid phase that we want to study and the kind of model that we use to study it. So just going back to the original proposals of the RVB state from Anderson, the system he was considering there was this system of spin 1-off particles on a frustrated lattice like the triangular lattice with antiferromagnetic interactions. So his idea was, due to the frustration, what the spins could do is to form these entangled pairs, also called dimers, that are the superposition of up-down and down-up. So all the spins in the lattice would form these dimers, and we can immediately see that there are several possible solutions for the pairings of the dimers, and so the ground state of this system would be the macroscopic superposition of all the possible dimer configurations on the lattice. And this is what he called this resonating valence bond state. So this gives rise to this quantum spin liquid phase where the spins are not ordered spatially, but there is this more liquid-like disordered phase. Now the question here is, can we realize something like this by using Rydberg atom arrays? And here I would say if we want to create something like this, probably the fact that the dimers are these entangled pairs of spins is not crucial for the creation of this RVB state. What is crucial is that we have these dimers that can occupy different type of configurations on the lattice, and so they give rise to this macroscopic superposition. So the idea here is if we take the triangular lattice here and we place our spins, our atoms, not on the vertices like in the triangular lattice here, but on the links of the lattice, and we have a Rydberg excitation at some point in the lattice. We have some blockade radius RB, so that the other excitations need to be at a certain distance from the first excitation. So what you see here is that if we map each of these Rydberg excitation to a dimer, we get to a situation that is very similar to what we have here. So the Rydberg excitations, like the dimers, need to be at a certain distance from each other. So they cannot touch each other. Each vertex can only be in one dimer at a time. And you also have multiple solutions, sorry, not yet, multiple solutions for these arrangements of Rydberg interactions. So it turns out that it doesn't really work for the triangular lattice. I'm kind of cheating here. You don't get this nice dimer model mapping. But a couple of years ago now, there were some study by two groups at Harvard where they looked into this idea of mapping dimer models using Rydberg atoms. And in these two papers, they saw that there are very interesting phases that come up with this using different types of frustrated lattices. And in particular, what I'm going to talk about today refers to the second model, and Ruben who's in the audience, is really the father of this very cool model that I'm going to talk about. So what is the idea of this model? The type of frustrated lattice that they use there is a so-called Ruby lattice, where the atoms are placed on the links of a Kagome lattice. So the lines that you see here correspond to a Kagome lattice, and the green dots, which are the atoms, are on the links of this array. Now what we can do is to tune the blockade radius such that when we have an excitation to the Rydberg state here in the red atom, the 6 nearest neighbors are all blockaded, and so the other excitations need to be at this distance. This provides a constraint on the maximum density of excitations that you have on the system, which is 1/4 of the total number of atoms. And this gives you a nice mapping onto the dimer model of the Kagome lattice according to this idea that I showed before. So each atom in the Rydberg state is mapped onto a dimer that connects the two adjacent vertices of the Kagome lattice. So again, when you have exactly 1/4 density, it means that each vertex of the Kagome lattice belongs to a single dimer. Okay, so what they saw doing the MRG simulations on this type of lattice was that there is indeed a range of parameters where there is a quantum spin liquid state, which again corresponds to the macroscopic superposition of all the possible dimer coverings of the lattice. And they showed that this state has Z2 topological order. Okay, so what we do in the experiment is very similar to what Misha showed before. We just shine all the atoms with these lasers that couple the atoms to the from the ground to the Rydberg state. And so we have a Rydberg Hamiltonian. And then when we look at the final state, after some state preparation that I will show you in a second, we find something like this. Again, here we perform imaging, we detect the atoms in the Rydberg state, and here I present them with these red dimers. And here you can immediately see a couple of things. The first one is that this is a pretty nice dimer covering, meaning that we have a density close to 1/4. If you look at each vertex on the Kagome lattice, you typically have a single dimer touching it. We only have a few holes here and there. And the second thing is that if you look at the dimers, you cannot really detect any obvious spatial ordering. So this looks to be in the right ballpark of what we expect to see. Now, how do we do the state preparation? So here we have the usual Rydberg Hamiltonian that Manuel and Misha showed before. And what we can do is we start with, we use delta, the detuning of the Rydberg transition, as our driving parameter. And we start in a situation where the detuning is negative and large. So here, the ground state of the many-body system is the one with everything in the ground state. And then we slowly change the tuning such that we slowly change the Hamiltonian to the regime where the expected ground state is the spin liquid. If we do this slowly enough, so in an adiabatic way, we expect the system to fall in the ground state of the instantaneous Hamiltonian. So this is in particular the ramp that we do. So we slowly turn on omega, so we slowly turn on the lasers. We start with a negative detuning and we do this cubic sweep of delta to go from the ground state with everything in the ground state to the final spin liquid. Now the first thing that we can measure is the density of excitations as a function of the final detuning. And what we see is that a negative detuning, we start with the density close to 0, and then as we ramp up the detuning, the density grows up to this point where around 1/4 filling, it starts to saturate and kind of slow down. So around here, where the density is close to 1/4 is where we expect to see the spin liquid. But of course, to characterize a topological phase, we need to probe some non-local correlations. And so we do that by measuring topological string operators. So very similar to what you would have in a toric core. So the way they're defined for our model is the following. We have a first string operator, Z, that corresponds to measuring the parity of dimers along a string. The string looks like this, like the green one here. It crosses the bonds of the Kagomel lattice. We measure the parity, meaning every time we cross a dimer, we get a -1. So for this small loop that I drew here, we would get an expectation value of Z of -1. And if you think about it, what I told you at the beginning is that if you have a perfect dimer covering, each vertex is touched by a single dimer, which means that for this small loop, you will always have an expectation value of -1 for a dimer covering. Now, if you extend this argument to a larger loop, you will see that, again, the expectation value will always be -1 to the number of enclosed vertices, just if you are exactly in this dimer phase. So measuring the expectation value of Z on closed loops is what allows you to detect if you are in a dimer phase or not. So how do we measure this in the experiment? We take a snapshot like the one that I showed you before, doing this fluorescence imaging. We detect where the dimers are, and then we start measuring, we start drawing these closed loops and measuring the parity on these kind of loops. We average over loops that are at different location on the array, and we also average over many different experimental repetitions. And here I am showing you the results for these two examples of closed loops. So here what we see is that at negative detuning, we have a trivial positive expectation value for both. This simply comes from the fact that the density of dimers here is very small. So you would expect here you have only a few dimers. So most of the times when you look at these loops, they would cross no dimers at all. So the expectation value would be +1. On average, you have more time a +1 than a -1. So you get a positive expectation value. But then when the density grows, this starts to average down to 0 until when the density is close to 1/4, it grows to a finite expectation value for both loops. And also it's interesting to notice that the sign for the two is different, because in this smaller loop we have 6 vertices inside, so an even number, whereas in this case we have 11, so an odd number. So according to this rule up here, we would expect a different sign. Now we can zoom in into this region and look at loops of different sizes and shapes, and we see that on this central region, on the central range of the tunings, we do observe a finite expectation value for all these loops, where the sign also matches with the parity of vertices inside. So from this first measurement, we can conclude that we're observing, in this range of the tunings, we're observing the transition to an approximate dimer phase, where the word approximate, of course, refers to the fact that the expectation values we measure are not perfectly 1 or -1, and they also decrease with the size of the loop, which means that we are in a dimer phase with a finite density of defects. So every time you have, for example, in the picture that I showed here, every time you have an empty vertex, like in this case, you will see that the expectation value flips to the wrong value. Okay. But what I told you before is that the spin liquid we expect is a superposition of dimer coverings. So we need to be able to measure the coherence to be sure that the state we're preparing is a spin liquid. And so to do that, we introduce the second string operator, which is the off-diagonal operator X. This is the way it is defined. Again, this is just a definition, so take it as it is. We define its action on a single triangle of the Kagomel lattice. And so when we act with X on this side, we would create or annihilate a dimer on that side of the triangle, and if the dimers are on the opposite sides instead, it would swap their positions. And now if you apply this definition to X on a closed loop, you will see that every time you apply X on a closed loop, you map a perfect dimer covering into another dimer covering. So for example, for this small dimer covering on a single star of the Kagomel lattice, this is a valid dimer covering. Now when you apply X on this hexagon, you would remove this dimer, create one here, remove this one, and so on, until you get to this complementary dimer covering. Same thing here, you apply X on the hexagon, you swap the position of all the dimers, and so you get to this configuration. So since applying X on closed loops maps dimer coverings into other dimer coverings, if we measure X on closed loops on the state we prepared, and we find a positive expectation value, this means that the state we prepared had a coherent superposition of the coverings that are mapped by that specific closed loop. So this is a way that we have to detect the presence of coherence in the state we're preparing. And the way we have to measure this in the experiment, this is actually a brilliant idea from Ruben. Since we usually measure in the Z basis, how do we measure this kind of complicated X operator? It turns out that you can measure X by applying a quenched time evolution to your state and then measuring Z on a dual string. So it turns out that this operation maps the expectation values of X on this string to the expectation values of Z on that dual string. So I won't go into the details here, but this just works. So the way we do this so the trick here is that this quench time evolution needs to happen with a reduced blockade radius. So remember before the blockade radius was larger, it included the 6 nearest neighbors, whereas here we have only the 3 atoms in the same triangle that are blockaded. So the way we do this in the experiment is after the state preparation, we want to apply this quench. So we change the tuning to go to resonance, and simultaneously we change omega such that we can change the blockade radius. And we apply this quench for a specific quench time that applies the basis rotation, and then we measure. So long story short, if we measure X on the loops that I plotted here, this is what we find. So as expected for the spin liquid, we see that X has a finite expectation value on a finite range of the tunings, which allows us to conclude that we do have signature of coherence between different dimer coverings in the phase we're preparing. Okay, so this is great, but we need one final thing to actually be sure that this is a spin liquid. And in particular, what we want to do is to compare the expectation values that we measure on closed loops, which is what we did so far, and open strings. So, for example, here I'm showing you the expectation value of Z on this open green Z string, and compared it with the closed loop that I showed you before. And here you see that in this trivial phase that I identified before, both of them are finite, whereas in this dimer phase that we identified earlier, you see that only the closed loop has a finite expectation value, whereas the open string goes to 0. And similarly for X, we see that small detunings, both of them give a finite expectation value, whereas later on here, only the red one stays at a finite value. So this tells us that the closed loops are the one that we want to look at to detect non-trivial topological correlations, but the open strings are useful because they allow us to distinguish the spin liquid phase that we're interested in from nearby trivial phases. And a more quantitative way to do this is to measure these so-called Rydberg and Markov order parameters, which measure the ratio between the open strings with the square root of the closed string. So in particular, what we expect from theory is that the spin liquid is the only phase where both of them give 0 expectation value, whereas in the 2 nearby trivial phases, which are the disordered phase at low detunings and a possible valence bound solid at higher detunings, one of them is instead finite. So we measure this in the experiment, and so here I'm plotting both the Z and X FM order parameter, and you see that we can identify a range of the tunings where the 2 FM order parameters are 0, whereas the closed loop expectation values are finite. And so this is where we identify the onset of a quantum spin liquid phase. So to recap, what we saw is that we have finite expectation values for the Z closed loops, finite expectation values for the X closed loop, which means that we are in a dimer phase with coherent superpositions of dimer coverings. And finally, we measure these FM order parameters to exclude nearby trivial phases. So putting all this together, we can conclude that we are observing the onset of this quantum spin liquid phase that we were looking for. So with this, I finished the first and the longest part of the talk. So if you have questions on this, this would be a good time. Otherwise, I will. Yes?
Giulia, I have to ask, so what's the current understanding in terms of the dynamical nature of what's going on? So as far as I know, the ground state in that model doesn't host the spin liquid at all. and you use the phrase phase a few times. So given that the ground states don't host the spin liquid, what do you mean with phase, or what's the understanding of what's actually going on in the experiment?
So you're correct. So our current understanding, and maybe Ruben can tell you more about this because I think there are some more recent updates. So our understanding is that so if when they do numerical simulations, including the 1/6 van der Waals potential, it looks like when you include long distance interactions, the spin liquid disappears and the ground state is this valence bound solid. And there is a first order transition from the trivial phase to this VBS phase. But nonetheless, we observe these correlations that cannot be attributed to a VBS phase. And so our current understanding is that the non-perfect adiabaticity of the way we do the preparation allow us to end up in some state that is not the ground state. It looks like a metastable state that actually looks like a spin liquid because it is the superposition of these many different dimer coverings. So in a sense, the non-perfect adiabaticity, it's what allows us to see this state. I think there is some more work that Ruben and some of the students in Ashwin group have done where they see that this is kind of a general mechanism where even in different kinds of models you can see something like that. One caveat is that what they saw is that if you slightly tweak the geometry of the lattice, you can indeed have a spin liquid which is in the ground state. And so this is something that we could try to do as well. But it's not obvious, at least to me, if it's something that we should do or if it's or if this is good enough. I think doing going through the first order phase transition would be very hard experimentally. Sorry? Well, I guess maybe it's maybe I shouldn't call it phase. It's a yeah.
Why not? No, BC is BC a phase? Or like huh? What? Yes or no? I mean, BC is exactly the same. It's a metastable state which has long lead time, but it's not a ground state. Right? So it's a phase, in the same sense. So there is actually, there is a negative. But there is basically, I think, we do here see some indications that it's a second order phase transition of what we see. And there is a competing first order phase transition, which we do not see unless we go exponentially slow. Yeah. In this phase which we can access. And I think there is a lot of now evidence from Ruben, but also Hannes with his here, that it really is what is happening.
Okay.
We have another question.
Okay, yeah.
So regarding the Fredenhagen-Markov autoparameter, my understanding is that for a finite size system, it's not actually zero. Yeah. But I'm not sure I'm seeing much finite size behavior. Have you actually tried fitting this to an exponential?
So I guess, so you're right. So the system size here is finite, and so we cannot really go to extremely long strings. What we see is that if we increase, so here what I'm showing is this order parameter on strings of increasing lengths. And what you see is that as you increase the length, this goes closer and closer to zero in this region. We haven't tried to fit it to an exponential, but I mean, we only have maybe 3, 4 of these, so I don't know how meaningful that would be, but yeah.
And do you have an expectation how big it should be on these finite size systems?
How big the expectation value should be, or how? No, I don't think. I mean, we can compare it to the simulations on similar, but the problem is that the simulations either have closed boundary conditions for a little bit larger system sizes, or they're very small if you have closed boundary conditions. So you cannot really simulate this size. So it's hard to say, I would say, from comparison with the, yeah.
Actually, I had a question as well.
Yes.
So they're systematically well below 0.2, 0.1. So what is the reason? Is it possible that the the string operator have rotated because you don't have the exact Hamiltonian, or?
Yeah, so I will actually comment on that towards the end of the talk, so maybe we can get back to that question at that point.
Any other question for this part? Okay.
Okay, let me go on. So quickly, I want to show you, of course, what you can do with this Z2 spin liquid is to use it to create a topological qubit. So I just want to show you the very first steps that we did in this direction. And what you want to do if you want to create a topological qubit is to have an array with non-trivial topology, which means that you need at least one hole. So that's exactly what we did. We removed a few atoms here from the center so that we have an inner boundary and an outer boundary of the array. And so when we do this, we create two distinct topological sectors for the dimer coherence of this array. And you can see that if you take these three examples of dimer coherence and you superimpose them in pairs, for example, in this case, you superimpose them, you remove the overlapping dimers. And so you are left with a few dimers that show you how does the transformation look if you want to transform one into the other. You will have to move around the dimers that are left here. If you do the same thing for this pair of dimer coverings, you will see that you are left with the loop of dimers that go around the hole. And so this tells you that these two belong to opposite topological sectors. And now if you imagine the array and the hole to be much larger, you see that to do the transformation, you need to involve a large number of dimers and a very non-local transformation because you have the hole in the middle, so you need to go around it. So this is an easy way of seeing how the dimer coverings split into two different topological sectors. And so you have this inherent topological protection, meaning that if you take one of these dimer coverings and you just flip one dimer and move it to another side, you will see that you remain within the same topological sector. But to go to the other one, you need to do this non-trivial, non-local transformation. So what we can do is to encode the two logical states of the topological qubit as, so we define 0 and 1 as the spin liquids that live in one or the other topological sector. And now we can define logical operators so we define sigma z as the z string, any z string that connects the hole to the outer boundary. And you can see that this is a good sigma z because if you look at any string, any such z string, you will see that they all have the same expectation value in the same topological sector, but the opposite one in the other topological sector. So here you have that the eigenstates are 0 and 1, the two logical states with eigenvalues +1 and -1. And for sigma x, we use this closed x loop that goes around the hole because here the eigenstates are the plus and minus states, which are the symmetric and antisymmetric superposition of the logical states, again with eigenvalues +1 and -1. So what we do here in the experiment is to use the same exact state preparation that we did before for the array without the hole. And now we measure these logical operators, and what we find is that in the spin liquid region that we identified before, sigma z is 0, whereas sigma x has a positive expectation value. So the state that we naturally prepare with this quasi-Diabati preparation has a finite overlap with this plus state. So these are the very first steps towards the creation of a topological qubit based on these spin liquids, but of course there is much more to be done to show how to encode and manipulate the qubit and possibly do entangling gates. And I will mention this a little bit towards the end. So now I want to show you this final part where we want to find out how we can enhance the detection of the topological order. As we were saying, we clearly see that the expectation value that we measure for x and z on closed loops are smaller than 1 and significantly smaller than 1, and they decrease with the loop size, which means that the state we're preparing is different from the fixed point of the dimer model. And this is due to both coherent perturbations and incoherent errors. So the question is, can we do something to enhance these measurements and to better detect the topological order? So for example, if you look at the snapshot that I showed you before, as I said, we immediately see a few defects in the Z basis. So we have these empty vertices that corresponds to E anion in the spin liquid. And so we can measure this, we can detect them by measuring the stabilizers on the proper Z plaquettes. So in this case, the Z plaquettes are defined as these diamonds that enclose a single vertex. And similarly, in the X spaces, we have these phase errors that correspond to M-anyons. We cannot detect them as obviously because when we do measurements, we do them in the Z basis, but we can do that by applying this rotation that I showed you before. And in this case, the plaquettes correspond to these hexagons where the M-anyons and these phase errors live. So the idea of this enhanced detection is to use, and this again is presented in this paper that will be on the archive hopefully in a week or so. The idea of this method is to use local error correction plus coarse graining, which mimics a way of recognizing phases similar to the RG flow. So let me show you how it works. First of all, we do error correction by pairing anyons. So here I'm showing you an example on the toric code, which is easier. So we take a snapshot and we pair anyons that are next nearest neighbors. So they are a distance 1 from each other, and we correct for them. So we flip the spins that correspond to those anyons. And then we do a first round of coarse graining. So we reduce the number of qubits. We end up with a coarser grid for the toric code. And again, we have some remaining anyons. We pair up the remaining anyons that are now nearest neighbors on this larger grid. And then we do another round of coarse graining and so on until we finally measure the Wilson loop, these loop operators on these coarse-grained array. And this corresponds, and this is equivalent to, so measuring the Wilson loop on this final array is the same thing as measuring the loop operators on these decorated or flattened loops. So this is an idea that is not new. This was already presented, for example, by these authors in 2005 and 2006. But what is new is the way we do this error correction coarse graining to define these flattened and decorated loop operators. So let me just briefly show you how we can apply this in post-processing to our experimental data. And so, for example, now we can consider these loops that are much larger than what I showed you before. Before, on loops of this kind, we would have a negligible expectation value. This would be very close to 0. But now, if you apply this correction with increasing correction distance, you see that we get to a finite and visible expectation value in the same region of the spin liquid that we identified before. And we can do the same thing in the X basis measuring closed X loops. You see now we have this very large loop. Here the plaquettes are much larger, so we can only do D equals 1. We cannot go larger. You see that here we're already touching the boundaries of the array. So to actually be able to do further corrections, we would need a larger array, but hopefully we will be able to do that soon. But again, you see that after applying the correction, the expectation values in the relevant region are increased. We can also do the same thing with open strings, and here we see that for these open Z strings, again, we see that we have no relevant correction, and in the spin liquid phase, they remain identically 0. Okay, so this gives us a new tool for probing topological order and actually can be extended to different models, and this is something that I think could be very powerful for other topological phases as well. So let me just give you a quick outlook so that I can conclude. Of course, what we would like to do is to improve state preparation and measurement. As I mentioned, we did these first steps with the topological qubit, but we have ideas on how to encode and manipulate the topological qubit by applying these logical operators, and this would require the addition of local addressing of some subsets of atoms, and for example, the ability of doing braiding experiments like this, where you localize an anion and you move it around the hole, for example, to do a braiding experiment. Another thing that we would like to do is to use this error correction idea to actually perform feed-forward error correction. So here we would add some ancilla atoms to measure the stabilizers in a non-destructive way and then annihilate the anions that we detect. And finally, something else that we're thinking about currently is how we can engineer alternating M and E boundaries with of this spin liquid to create non-abelian ions at the edges, and if we can do something interesting with that. So finally, as Misha mentioned before, we are now doing a pretty substantial upgrade to the atom array experiment. So it's going to be generation 3. So I would just quickly flesh this out. The main goals are to achieve larger arrays with about 1,000 atoms, faster cycle times. We want to reach higher fidelities for both the entangling gates, the initialization of the qubits, but also the state detection. We are adding some local control capabilities, and also we are working towards the implementation of mid-circuit readout for quantum error correction. Finally, let me, in 5 seconds, mention that there's also going to be a new atom array experiment at Harvard in my own group starting in July. And the idea would be there to have a 2-species atom array combining alkyl and earth atoms. As you heard yesterday from Manuel, this can give access to some interesting new tools with alkali atoms, so that you could have different types of qubits that you can take advantage of in mixed architectures. You can have selective control of ancilla and data qubits. And then you also have some new tools for quantum simulation of many-body Hamiltonians. So with this, again, this is the team. And also let me acknowledge the many amazing theory collaborators that we have that have certainly helped a lot with these experiments. And with this, thank you, and I'm happy to take any questions.
Okay, I have actually a question, because I asked the question and then you promised that
I didn't answer. So
I probably missed the enhancement. So once you do this coarse graining, wouldn't the expectation value of Z and X should increase?
Yeah, so this is what you see, for example, in these 2 pictures, what you see is, well, we don't have D equals 0 here, but when you don't do the correction, basically you don't see any, like the expectation value is very close to 0. And when you apply 2 or 3 layers of this correction, you see that there is this enhancement of the Z expectation value.
In the science paper, it was at least 0.1.
Yeah, but this is a much larger loop.
Ah, okay.
So yeah, we're not plotting it for the other ones. You would see the same thing. They start from a finite value and they're enhanced. Here we're showing it on this more extreme loop that is almost the same size of the array. So it shows that you have these topological correlations towards the entire.
Yes, for the bigger loop and for enough layers, it should flow to 1. But of course, it requires bigger system.
Yeah.
Okay.
It flows in the right direction. That's
nice. Okay. Thanks. Any other question, Michael?
Yeah, I'm just wondering, you're talking about error correction. I guess, do you have these kind of like systems level analysis of this Rydberg array, really accounting for all sources of errors and computing thresholds, things like that? Or is that's not the approach here?
Sorry, I didn't get the question. Again.
Yeah, I'm just wondering if you've done sort of more systems level analysis, like is this really a system we should scale up for quantum computers, or what's the perspective on that?
So you're talking about the spin liquid and the topological qubit itself, or the atom array in general?
Just I guess you're moving in the direction of error correction.
Yeah.
I'm just curious about, the scalability issues and really more systems level.
Okay, so on this specific model here for the spin liquid, honestly, I don't think that this is the best strategy to do, encoding of qubits and error correction. I think this is a quite intricate system that is probably not the most advantageous. But I think what Misha was talking about with this atom moving experiment and that kind of thing, that looks like a much more scalable solution to that. I think this is more interesting because of the physics, and here you have these topological physics that are actually encoded in the Hamiltonian of the system itself. So it has more fundamental interest to me than the applications themselves. It's a face.
Okay. Let's thank Giulia and Misha for this interesting session of Rydberg.